morning, everyone. Today we're going to be talking about testing of thermal energy storage using reverse osmosis concentrate, also known as TESuROC. I'm Narag.
I'm Andrew Wilson.
Our advisor is Dr. Reza Lakeh, and we're with the Mechanical Engineering Department.
Okay, so in our presentation, we're going to go over our background and motivations, the TESuROC solution that's thermal energy storage using reverse osmosis concentrate. We did a techno-economic cost analysis. We go over the methodology of our test, our data and results, our conclusions, and then our future work. Okay, so if you look on the right side here, you can see a typical steam power plant. There's a turbine that produces work, there's a condenser, and it's pumped back into the steam generator right here, where it's heated back up, so it can cycle back to the turbine. Now, unlike most steam power plants, this one isn't fueled by coal or natural gas that heats up the steam generator. This one has a solar field that produces heat to heat up the steam generator. So what happens here is a heat transfer fluid, typically in oil, runs to the solar field, gets heated up, and then heats up the steam generator so the power plant can operate. Now this works fine during the day, but at nighttime when the sun goes down, what they do is they put some of the heat from the solar field into thermal energy storage so that we can run the power plant at night. And when the sun goes down, the heat from the thermal energy storage, or TES, goes and heats up the steam generator so the power plant can keep on running. Okay, and the motivation of this project is the Sunshot Initiative. It's a Department of Energy goal to get the cost of concentrating solar power down to 5 cents per kilowatt hour electricity generation by the year 2030. And $15 per kilowatt hour for thermal energy storage. Okay, so now we're going to change up a little bit. We're going to talk about reverse osmosis concentrate. Reverse osmosis. Reverse osmosis is a process where a contaminated water is run through a semi-permeable membrane, and it produces pure potable water and a concentrated brine. Now, the issue with this is the concentrated brine is hazardous waste, and the ways that they typically get rid of it are surface water discharge or deep well injection, and both these are hazardous to the environment. And you could also do salt extraction, which is what we're going to look into. And so what our suggested solution is you use the salts from this reverse osmosis concentrate as a low-cost thermal energy storage medium. So this solves two problems at once. We get rid of the harmful reverse osmosis concentrate, and we have our low-cost thermal energy storage medium. And this thermal energy storage could be used for space heating, process heating, or like we mentioned before, power plants. So to do this, there's a few costs associated with it. We have transportation costs right here. We need to take the reverse osmosis concentrate from where it's produced to a facility where we can process it. And then we evaporate all the water out, so we're left with just the salts. Then we have to grind the salts, and then we need a container to hold the salts to be used in thermal energy storage. But we also have a gain, because as we mentioned before, reverse osmosis concentrate is a hazardous waste. People will pay you to dispose of it for them. And so now we're going to look at some of the relative costs of thermal energy storage medium. So right here we have water, and as you can see, water is very cheap. But because of the high temperatures and pressures associated with thermal energy storage, the containment costs are very high. You have to have a very thick walled vessel to carry it. Now, what they also use more typically is molten salts. Now, molten salts are much more expensive than water, but like I said, the containment costs are much lower than the containment costs for water. So it ends up being cheaper overall. And what we're proposing you do right here has about the same containment costs as thermal energy storage, thermal energy storage using typical molten salts. And we also have the processing costs right here that we mentioned. But since we said that companies will pay you to dispose of their reverse osmosis concentrate, we have our gain, or negative costs. And so we did a cost analysis where we went through and looked at the transportation costs, evaporation costs, grinding costs, containment costs, and then the gain. And we looked at it for storage at different temperatures, 400 degrees Celsius, 600 degrees Celsius, 800, and 1000. And 800 degrees Celsius was our baseline. And as you can see, 600 degrees Celsius, 800, and 1,000 all came in under the $15 goal for Sunshine Initiative. And our baseline was $8.96.
So now we're going to go into the proof of concept for our TES system. We wanted to design a testing apparatus that could simulate a real-world application. So in our setup, we have a heater and blower, that's attached to our TES testing element, which has the salt tube integrated into it, which is filled with our ROC salt. And we also have a heat exchanger and exhaust system for dissipating heat. By blowing air through the system, we simulate the charging and discharging of thermal energy, as we would see in a real-world application. Furthermore, we did a a melting degradation test to measure the storage potential of the ROC salts. So for data acquisition, we used a variety of thermocouples to measure the temperatures of the air, the containment, and the salts within the tube. We also used a flow meter to measure the volumetric flow rate. And we used a data acquisition system to record data at intervals of 20 seconds. So here's our setup. This is a TES element. This is our heater and flow meter. And this is our data acquisition system with the thermocouples attached. So now we're going to talk about the methodology of the tests for the thermocycling experiment. It consists of a charging and discharging phase, where we hold the mass flow rate of the system constant. We also heat the air at the inlet of the heat exchanger to a constant temperature, and we continue to heat the system until we reach steady state. Once we reach steady state, we allow the system to cool, and we continue to cool until the temperature difference the air temperature difference is equivalent to 0 at the inlet and outlet. So here's our data plotted versus time for the air internal and external thermocouples. As you can see, this is where the charging phase begins. It begins to plateau, and then when we start our discharging phase, it dramatically decreases. So to actually analyze this data, we have to make a few assumptions. We have to assume that the system is isobaric, meaning that the pressure throughout the system is constant. We also have to assume that the mass flow rate going through the system is constant from the inlet to the outlet. And we also have to assume that air is an ideal gas. So the energy stored in the TES element can be represented with this equation, which states that the energy stored is equivalent to the thermal energy of the air at the inlet minus the thermal energy of the air at the outlet. Furthermore, we can separate the experiment into the charging and discharging phase, and it can be represented with these two equations, which is just the simplified equation for thermal or steady state or steady flow thermal energy and the ideal gas law. So plotting our temperature data into those equations, we get this graph. Notice how we exclude this middle portion in our analysis. We exclude that portion because we are, at that point, we reach steady state. So any additional heat input we put into the system, we immediately dissipate it out into the environment. So we exclude it. So taking the area underneath this curve, we get that the thermal energy stored during the charging phase is 114 megajoules. The energy stored, or the energy discharged is 48 megajoules. And then plugging it into the efficiency equation, we get an energy storage efficiency of about 42%. Furthermore, we mentioned a salt degradation test. We wanted to see that the ROC salts consistently melted at a certain temperature, which is critical for applications where you're charging and discharging the salts. So we found that the ROC salts would melt at about 550 degrees Celsius to 650 degrees Celsius. So as a whole, ROC salts are a very promising solution for thermal energy storage. With our techno-economic analysis, we found that the costs were underneath the required $15 per kilowatt hour, and we found that our thermal energy storage is 42%, which is promising because we expect higher efficiencies with the molten salt. So for future work, we hope to redesign our system. We hope to do time-dependent energy storage tests, and we also hope to ultimately compare these results to industry standard salts. Right. So we'd just like to mention a few acknowledgements. Our project was funded by the U.S. Department of Interior, Bureau of Reclamation. We'd also like to make a special thanks for the Eastern Municipal Water District and Chino Basin Desalter Authority for our salts, and our lead technician, David Lakeh, and obviously the Mechanical Engineering Department. Thank you.
We can have a couple of questions. Okay, let's start with
Okay, it's actually a two-part question. One is, are there any existing systems that use this thermal energy storage currently in use? And then secondly, did you assume a cost that these reverse osmosis plants would pay for you to take their salts to determine if it was financially viable?
So yeah, for the first question, if there are any existing systems, our testing apparatus is unique, where we're simulating a real-world application, but in place in current concentrating solar plants, they use different molten salts. So the technology for the molten salts are there, but not specifically for ROC salts. The second part of the question is the cost associated with the ROC salt.
Them paying you to take their brine.
I believe in. So we were expecting, I guess, different. Well, we found a certain amount of gain depending on where we got our salts from, and we compared the gain with. We did sensitivity analysis with all of our other factors to see whether or not it was actually financially viable. So we would change parameters in our evaporation, transportation, our grinding, and containment, and then we'd find whether or not it was financially viable. Does that answer your question?
Generally,
yeah. A few. So first off, what, I guess, kilowatt size or scale would this technology be most applicable? What are you looking specifically at power plants, or can the system be modeled down for any type of solar energy storage applications?
So typically, we think it would mostly be used in power plants, just because of the high temperatures that sun-John initiative wants. The high temperatures associated with sun-John initiative, and
yeah. So ultimately, we want to use these technologies in power plants.
Okay.
Because at that scale, the temperature difference that we're hoping to achieve is because you're scaling up, it's much more effective. Whereas at smaller scale, you wouldn't see as much of an efficiency gain.
Sure. And how does your thermal efficiency compare to like molten salt or other ceramic energy storage technologies that are currently being used in the market?
So that is why in future work we hope to actually use molten salts in our testing apparatus, so we have a better comparison. So we're not comparing against concentrated solar plant efficiency numbers. We're comparing with our specific testing apparatus.
Gotcha. And then just a small plug, if you are considering moving forward just beyond this research project with this technology, please approach me after the presentations. I think I might have some resources that could be pretty applicable to your situation.
Thank you for the plug.
Yeah.
Okay, I have to stop here and have to thank our presenters, so let's give them a hand.